October 15th, 1895, Cincinnati, Ohio. The insurance assessor's report would never fully capture what the fire had destroyed that morning. American machine tools, built using methods that defied everything European engineering traditions said was necessary for precision manufacturing. Through the smoke and ash of the ruined factory floor, the remains of revolutionary milling machines lay twisted and melted, machines that had operated continuously for over 800 hours without losing accuracy. European competitors celebrated. Swiss and German manufacturers had always insisted that American speed came at the cost of durability. Their apprentice-trained craftsmen required decades to master precision work. Their machines, built with time-honored methods, represented centuries of refined tradition. The Americans were rushing everything, overbuilding components, simplifying controls, abandoning proven European designs. Yet before the fire, these same American machines had outperformed every European competitor. Heavier construction, centralized controls, precision that lasted not months, but decades. 900 miles from European workshops, the most decisive manufacturing revolution in industrial history was being tested by flames. Not in superior craftsmanship, not in traditional methods, but in the systematic overengineering that made American machines virtually indestructible, in ways European precision traditions never imagined possible. The morning mist hung thick over Narragansett Bay as Joseph Brown stepped through the mahogany doors of his Providence factory on November 3rd, 1882. At 52, his calloused hands still bore the precision of a clockmaker's apprentice, fingers that could detect variations measured in 10,000ths of an inch by touch alone. The Brown and Sharp Manufacturing Company occupied 4 brick buildings along the Providence waterfront, their smokestacks releasing steady streams of coal smoke into the Rhode Island dawn. Inside, the rhythmic hammering of steam-powered trip hammers mixed with the high whine of leather belt-driven lathes, creating the industrial symphony that had become America's signature sound. 900 miles west, in the growing industrial district of Cincinnati, Fred Holes arrived at his modest tool shop before sunrise, as had become his habit since inheriting the business from his deceased partner 2 years earlier. At 34, the German immigrant still spoke with the clipped precision of his homeland, but his restless energy belonged entirely to America. The Cincinnati Screw and Tap Company occupied a single brick building on the banks of the Ohio River, where paddle wheel steamers deposited iron castings from Pittsburgh foundries and carried finished machine tools downstream to factories in Louisville and New Orleans. Both men faced the same crushing reality that November morning. American manufacturing was losing the precision war against European competitors, and the consequences reached far beyond factory profits. In the previous year, Remington Arms had lost a $40,000 contract to Birmingham, England, because American-made rifle barrels showed inconsistent bore dimensions that British machines maintained with mathematical regularity. Colt manufacturing faced similar humiliations, with Swiss-made components outperforming American equivalents in side-by-side military testing. The humiliation stung deeper because these were American companies, founded on American innovation, now acknowledging European technical superiority. The problem lay in fundamental philosophical differences between European and American approaches to precision manufacturing. Swiss machine tool builders followed apprenticeship traditions dating to the 16th century, where master craftsmen spent 7 years training successors in techniques that prioritized absolute accuracy over production speed. German manufacturers like Ludwig Lohe and Company produced milling machines that could maintain tolerances of 1,000th of an inch for months of continuous operation, but required operators with years of specialized training to achieve such results. English firms like Herbert Limited built lathes that lasted decades, but their intricate adjustment mechanisms demanded constant attention from skilled mechanics who understood the subtle relationships between cutting speed, feed rate, and material behavior. American manufacturers had tried copying European designs, but the results proved consistently disappointing. Heinrich Weber, the Swiss-trained foreman at Providence Tool Company, summarized the prevailing European view with characteristic bluntness during a November meeting of the Rhode Island Manufacturers Association. "Americans rush everything," he declared, his accent lending authority to words that stung because they contained uncomfortable truth. Precision requires time, tradition, proper apprenticeship. These colonial tinkerers will never match European craftsmanship. Weber's own machines, imported from Zurich at considerable expense, demonstrated his point daily. Operating with hand-filed gears and individually fitted bearings, they achieved tolerances that American-built equivalents could not match. The stakes became undeniably clear following the devastating Springfield Armory tests of October 1884. Colonel James Ripley, the Army's chief of ordnance, had commissioned a comprehensive evaluation of American versus European machine tool capabilities. 5 American-built milling machines competed against 3 European models in a punishing endurance test designed to simulate actual production conditions. The requirement seemed straightforward: maintain cutting accuracy of 0.02 of an inch, while machining steel components for 200 continuous hours. The results shattered American confidence. All 5 domestic machines failed the tolerance test before reaching the 200-hour mark, with spindle bearings showing measurable wear and cutting heads developing wobble that rendered precision work impossible. The European machines, a Swiss Micron, a German Traub, and an English Herbert, maintained acceptable accuracy throughout the full test period, with the Swiss machine showing virtually no measurable degradation after 500 hours of operation. The War Department's official report, distributed to major American manufacturers in late October, delivered a verdict that threatened the foundation of American industrial ambitions. American tool-making appears inherently inferior to established European methods. Current domestic production capabilities cannot meet military precision requirements for sustained operations. The memo recommended sourcing critical machine tools from European suppliers, effectively acknowledging that American manufacturing had reached the limits of its technical capabilities. Brown received his copy on a gray Providence morning that matched his darkening mood. He spent the afternoon walking the factory floor, observing his Universal Mills cutting gear teeth and rifle barrel spirals with the steady precision that had built his company's reputation. Each machine represented months of development work and thousands of dollars in tooling investment. The operators, skilled men who had learned their trade in American factories, produced work that met commercial standards and satisfied most customers. Yet European standards now defined acceptable performance, and by those measures, American capabilities fell demonstrably short. That evening, as gas lamps flickered to life along the Providence waterfront, Brown made a decision that would reshape American manufacturing. Standing in his cluttered office, surrounded by technical drawings and precision instruments, he voiced the conclusion that had been building throughout that difficult day. "We're building the right machines wrong," he told his foreman. "Time to rebuild them right." Brown's revelation transformed his approach to machine design during the harsh winter months of 1885. Instead of copying European specifications, he began systematic analysis of why American machines failed under sustained operation. The answer emerged through methodical examination of bearing surfaces, spindle assemblies, and base castings retrieved from the Springfield Armory tests. European machines succeeded not because of superior craftsmanship, but because their designers understood the mathematical relationship between component size, material stress, and operational longevity. Working by gaslight in his Providence drafting room, Brown calculated the forces acting on machine tool components during typical manufacturing operations. A standard milling machine spindle, rotating at 800 revolutions per minute while cutting steel, generated radial loads exceeding 2,000 pounds per square inch on bearing surfaces. European designers accommodated these forces with bearings sized according to formulas developed through decades of empirical testing. American manufacturers, focused on reducing costs and manufacturing complexity, consistently undersized critical components by 20 to 30%. Brown's solution violated every principle of economical machine design. Where European mills employed 2-inch spindle bearings, he specified 4-inch assemblies with bronze races and hardened steel balls manufactured to tolerances of 5/10,000ths of an inch. Standard practice called for cast iron bases weighing 800 pounds. Brown's designs required 1,200 pounds of gray iron with mounting surfaces ground flat to within 2/10,000ths of an inch across their entire length. Every gear, shaft, and adjustment mechanism received similar treatment, oversized, overengineered, and manufactured to specifications that his own cost accountants declared commercially suicidal. The financial implications terrified Brown's business partners. A European equivalent milling machine sold for $180 and weighed 1,200 pounds. Brown's redesigned version required $340 in materials alone and weighed 2,100 pounds. The additional weight necessitated heavier floor supports, stronger overhead drive systems, and reinforced foundations that added hundreds of dollars to installation costs. Samuel Darling, Brown's longtime business partner, confronted him during a heated February meeting in the company's mahogany-paneled boardroom. "You're pricing us out of the market," Darling warned, spreading cost projections across the conference table. "Cincinnati Machine Tool sells comparable mills for $220. Our price point puts us in competition with imported Swiss equipment." The numbers supported Darling's concerns. Brown and Sharp had built their reputation on producing precision tools at prices American manufacturers could afford. The new designs threatened to eliminate their competitive advantage entirely. Brown's response reflected the philosophical transformation that would define American manufacturing for the next century. "We're not pricing ourselves out of the market," he replied, his voice carrying the certainty that came from mathematical analysis rather than market speculation. "We're pricing ourselves into permanence." He understood what his partners had not yet grasped, that initial purchase price meant nothing compared to operational costs over decades of service. A machine that required major overhauls every 3 years actually cost more than equipment that ran without significant maintenance for 20 years. Through 1886 and 1887, Brown subjected his redesigned mills to testing that bordered on industrial torture. Operating under double normal cutting speeds for 500 continuous hours, the machines endured conditions that would destroy conventional equipment within weeks. Brown documented every measurement, recording spindle runout, bearing temperature, and cutting accuracy at 50-hour intervals. His notebooks, filled with precise handwriting and detailed sketches, chronicled the gradual validation of his overbuilding philosophy. By January 1888, the data supported Brown's convictions with mathematical certainty. His redesigned universal mills maintained cutting accuracy of 1/10,000th of an inch after 800 hours of continuous operation, nearly 4 times the endurance demonstrated by standard American machines, and 60% longer than the best European equipment. The bearings showed minimal wear, the spindles maintained perfect concentricity, and the massive cast iron bases prevented the microscopic deflections that accumulated into major accuracy problems over extended periods. The breakthrough came through Brown's understanding of metallurgical principles that European designers had ignored. Instead of relying on traditional materials and heat treatment methods, he specified components hardened to Rockwell 58, a level that required specialized furnaces and precise temperature control. Every gear tooth received individual attention, with cutting edges ground to final dimensions after heat treatment to eliminate the distortions that occurred during the hardening process. Adjustment screws, typically made from unhardened steel, received chrome plating and precision threading that eliminated backlash and wear under repeated use. The manufacturing process itself required complete reorganization of Brown's Providence facility. Traditional machine tool production relied on skilled craftsmen who fitted components through careful handwork, filing bearing races and adjusting clearances until moving parts operated smoothly. Brown's approach demanded measurement-based assembly, with components manufactured to specifications that eliminated the need for individual fitting. He installed precision grinding equipment capable of holding tolerances measured in 10,000ths of an inch, transforming his factory floor into something resembling a scientific laboratory more than a conventional machine shop. The validation process extended beyond mechanical testing to include real-world applications that proved the commercial value of his engineering philosophy. Winchester Repeating Arms, facing quality problems with rifle barrel production, agreed to evaluate one of Brown's redesigned universal mills alongside their existing European equipment. Operating under identical conditions while machining identical parts, the Brown machine produced rifle barrels with bore dimensions that varied less than 5/10,000ths of an inch across entire production runs. More importantly, The machine maintained this accuracy without adjustment or maintenance beyond daily lubrication. By the summer of 1888, orders began arriving from manufacturers who had initially dismissed Brown's prices as commercially unrealistic. The Watertown Arsenal, responsible for producing artillery components for the U.S. Army, placed an order for 6 universal mills after witnessing demonstration cuts that achieved tolerances their European machines could not match. Baldwin Locomotive Works, America's largest steam engine manufacturer, requested detailed specifications for machines capable of handling the massive steel forgings required for locomotive construction. The transformation of American machine tool manufacturing had begun, driven not by patriotic sentiment or protective tariffs, but by engineering principles that recognize the mathematical relationship between initial investment and long-term operational success. Brown's Providence Standard represented more than improved manufacturing techniques. It embodied a fundamental shift in American industrial thinking that would reshape global competition for generations to come. While Brown perfected mechanical durability in Providence, Fred Holtz confronted an entirely different challenge in his Cincinnati workshop during the spring of 1885. His milling machines achieved acceptable precision, but American factory workers despised operating them. European-style controls, designed by craftsmen for craftsmen, required operators to manipulate dozens of adjustment levers scattered around the machine's perimeter, while simultaneously monitoring cutting speeds, feed rates, and depth settings. A typical milling operation demanded 3 hands and the spatial awareness of a trained juggler, forcing operators to stretch across spinning machinery to reach critical controls. Holtz observed this operational nightmare daily as he walked his factory floor, watching skilled machinists struggle with equipment that seemed designed to frustrate rather than assist human operators. European machines positioned the spindle speed control on the left side, the table feed mechanism on the right side, and the vertical adjustment wheel at the operator's back. Changing cutting parameters during operation required a dangerous dance around moving machinery, with operators frequently abandoning optimal settings rather than risk injury reaching for inconveniently located controls. The problem extended beyond mere inconvenience to fundamental questions of manufacturing democracy. European apprenticeship systems produced master machinists who understood these complex control arrangements through years of training, but American factories employed workers with diverse backgrounds and varying skill levels. German immigrants brought some mechanical knowledge, Irish workers learned through informal apprenticeships, and native-born Americans often acquired skills through trial and error rather than systematic instruction. European machine designs assumed operators possessed knowledge that simply did not exist in American manufacturing environments. Holtz's breakthrough emerged from his immigrant's perspective on American industrial culture. European workshops organized around individual master craftsmen who maintained personal relationships with their tools. But American factories demanded equipment that ordinary workers could operate effectively after minimal training. The solution required abandoning European assumptions about operator expertise and designing machines that made precision accessible to common sense rather than specialized knowledge. Working through the summer of 1885, Holtz developed what would become known as the centralized control concept, instead of distributing adjustment mechanisms around the machine. According to mechanical convenience, he positioned every operational control within arm's reach of a single station. Spindle speed, table movement, cutting depth, and feed rate adjustments clustered around the operator's normal working position, eliminating the dangerous reaching and stretching that characterized European designs. The innovation extended beyond mere control placement to include visual feedback systems that European designers had never considered necessary. Holtz added micrometer dials to every adjustment mechanism, allowing operators to make precise settings through numerical readings rather than mechanical intuition. Depth stops prevented overcutting. Automatic feed mechanisms maintained consistent cutting speeds, and clearly marked indicators showed spindle rotation and table position at all times. The result transformed milling machine operation from a craft requiring years of experience into a skill that competent workers could master within weeks. Holtz's own employees initially resisted the changes with surprising vehemence. Carl Steinberg, his most experienced machinist, had learned European methods during the Civil War and maintained that proper milling required listening to the metal speak rather than relying on mechanical indicators. During a heated August confrontation in the Cincinnati workshop, Steinberg voiced the objections that Holtz would hear repeatedly over the following years. "This isn't how milling machines work," Steinberg insisted, his weathered hands gesturing toward the traditional European equipment that had served the shop for 15 years. "You can't just reinvent 50 years of development because American workers won't learn proper techniques." Steinberg's concerns reflected genuine expertise rather than stubborn conservatism. European methods had produced consistently excellent results for decades, and abandoning proven techniques for untested innovations seemed commercially reckless. Holtz's response demonstrated the confidence that immigrant entrepreneurs often brought to American industrial challenges. "Watch me," he replied, his German accent lending authority to words that might have sounded arrogant from a native-born manufacturer. He understood something that his critics missed, that mechanical systems should adapt to human capabilities, rather than demanding that humans adapt to mechanical limitations. The crucial test came during the fall of 1889, when Baldwin Locomotive Works in Philadelphia issued a manufacturing challenge that would validate or destroy Holtz's operational philosophy. The contract called for 100 steam engine cylinder heads, each requiring 47 different machining operations with final tolerances of 0.02 of an inch across all critical dimensions. European practice suggested this work required 6 hours per piece, using master machinists trained in traditional methods. Holtz promised delivery in 2.5 hours per piece, using operators with standard factory experience. Samuel Morrison, Baldwin's chief engineer, had built his reputation on meeting impossible deadlines under intense pressure, but Holtz's claims seemed to violate fundamental principles of precision manufacturing. Morrison traveled to Cincinnati in November 1889 to observe the proposed manufacturing process, bringing with him the skepticism that experienced engineers developed toward revolutionary promises. What Morrison witnessed in the Cincinnati workshop challenged every assumption about the relationship between operator skill and manufacturing precision. 6 workers of varying experience levels operated Holtz's centralized control mills with confidence that seemed impossible given their limited training. The machine's intuitive design allowed operators to make complex adjustments without taking their attention from the cutting operation, while visual indicators provided continuous feedback about dimensional accuracy and tool condition. The demonstration revealed the profound difference between European craftsmanship traditions and American systematic approaches to manufacturing problems. European methods relied on individual expertise accumulated through years of apprenticeship, while Holtz's design embedded operational knowledge into the machine itself. Operators still required skill and attention, but the equipment guided their decisions rather than demanding that they discover optimal settings through experience and intuition. Morrison's initial skepticism gradually transformed into professional admiration as he observed the Cincinnati machines maintaining consistent precision throughout extended operations. The centralized controls eliminated operator fatigue, the visual indicators prevented common adjustment errors, and the overall design philosophy made precision manufacturing accessible to workers who could never have mastered traditional European techniques. By December 1889, Morrison had seen enough to recommend that Baldwin Locomotive Works place a substantial order for Cincinnati milling machines, marking the first major victory for American operator-centered design philosophy over European craftsman-centered traditions. The demonstration that would transform American manufacturing forever began at 7 o'clock on the morning of February 12, 1890, in the cavernous machine shop of Baldwin Locomotive Works in Philadelphia. Samuel Morrison had arranged the most comprehensive head-to-head comparison in American industrial history, pitting European precision against American innovation under conditions that would settle the question of manufacturing supremacy once and for all. 6 operators of varying skill levels stood ready to machine identical locomotive cylinder heads, using equipment that represented 2 fundamentally different approaches to precision manufacturing. 3 operators worked at European micron milling machines, imported from Switzerland at considerable expense and widely regarded as the world's finest precision equipment. The Micron mills embodied centuries of European craftsmanship tradition, with hand-fitted bearings, individually adjusted components, and control systems that demanded intimate familiarity with mechanical relationships, developed through years of apprenticeship training. The remaining three operators faced Holtz's revolutionary Cincinnati mills, with their centralized controls and operator-friendly design philosophy that European critics dismissed as mechanical gimmickry, unsuited for serious precision work. Morrison had structured the test to eliminate variables beyond machine capability and operator interface design. All six-cylinder heads came from identical Baldwin castings, machined to the same preliminary dimensions and requiring 47 identical operations to reach final specifications. The tolerance requirements pushed both machine types to their limits. Critical bore dimensions had to maintain accuracy within 0.02 of an inch, while mating surfaces required flatness within 5/10,000ths of an inch across their entire area. The first hour revealed the traditional advantages of European manufacturing philosophy. The Micron operators, all trained in Swiss apprenticeship methods, utilized superior cutting speeds that their intimate knowledge of the machines made possible. They adjusted spindle speeds and feed rates with subtle precision, listening to cutting tool behavior and responding to vibrations that less experienced operators could not even detect. Their cylinder heads emerged with surface finishes that reflected decades of accumulated craftsmanship knowledge, demonstrating why European methods had dominated precision manufacturing for generations. Meanwhile, the Cincinnati operators struggled with unfamiliar equipment despite the machine's operator-friendly design. The centralized controls simplified adjustment procedures, but the workers needed time to develop confidence in visual indicators that replaced the auditory and tactile feedback methods they had learned through traditional American apprenticeships. Their initial cutting operations proceeded cautiously, with frequent stops, to verify dimensions and adjust parameters according to micrometer readings rather than mechanical intuition. By the third hour, the fundamental differences between European craftsmanship and American systematic approaches began revealing their long-term implications. The Cincinnati machine's intuitive control layout allowed operators to make complex adjustments without losing focus on cutting operations, while the Micron mills demanded constant attention shifts between widely separated control mechanisms. More significantly, the Cincinnati operators showed steady improvement as they gained familiarity with their equipment, while the European-trained workers had already achieved peak performance levels that their superior individual skills made possible. The sixth hour marked the critical turning point that Morrison had anticipated but hardly dared expect. Cincinnati machines pulled decisively ahead in both productivity and consistency, with operators demonstrating confidence levels that seemed impossible given their limited experience with the equipment. The centralized control philosophy had eliminated operator fatigue that accumulated during complex multi-operation machining sequences, while visual feedback systems prevented the small errors that compounded into major dimensional problems over extended production runs. Morrison's carefully documented measurements revealed the mathematical validation of American manufacturing democracy. The European method produced cylinder heads averaging 6.2 hours each, with final tolerances averaging 1 5/10,000ths of an inch deviation from specifications. Individual pieces varied significantly depending on operator skill and attention levels, with the best work approaching perfection while less successful attempts required extensive rework or scrapping. The Cincinnati method achieved dramatically different results that challenged fundamental assumptions about the relationship between operator expertise and manufacturing quality. Average production time dropped to 2.8 hours per cylinder head, while dimensional accuracy improved to 1.2 thousandths of an inch average deviation. Most remarkably, the consistency between individual pieces far exceeded European results, with standard deviation measurements indicating that Cincinnati produced components required minimal selective fitting during assembly operations. The defect rate comparison provided even more compelling evidence of American manufacturing superiority. European methods produced reject rates of 3.2%, requiring expensive rework or replacement of components that failed final inspection. Cincinnati methods achieved 1.1% rejects, with most failures traceable to material defects rather than machining errors. The improvement translated directly into cost savings that more than compensated for higher initial machine prices. But Morrison understood that laboratory demonstrations meant nothing without validation under actual production conditions. Through March and April of 1890, Baldwin operated both machine types continuously under factory conditions, producing locomotive components for actual customer orders rather than controlled test pieces. The extended evaluation revealed performance differences that single-day demonstrations could never capture. European machines maintained their precision through the first 18 days of continuous operation, but accuracy gradually degraded as bearing clearances increased and adjustment mechanisms developed backlash from repeated use. By day 24, the Micron mills required daily recalibration by master mechanics who understood the subtle adjustments necessary to maintain dimensional accuracy. The intervention added substantial labor costs while reducing available production time for actual manufacturing operations. Cincinnati machines told a completely different story of mechanical endurance that validated Brown's overbuilding philosophy through practical application. After 30 consecutive days of three-shift operation, Holz's mills maintained their original precision without significant intervention beyond routine lubrication and normal maintenance procedures. The massive bearings showed minimal wear, the centralized control mechanisms operated with their original precision, and dimensional accuracy remained within specifications that European machines could achieve only under optimal conditions with expert adjustment. The moment of ultimate validation came in March 1891 when Baldwin Locomotive Works placed the largest machine tool order in company history, 24 Cincinnati milling machines worth $18,000. More significantly for the future of American manufacturing, Baldwin simultaneously canceled pending orders for European equipment worth $18,000, effectively acknowledging that American systematic approaches had superseded traditional European craftsmanship methods. By 1894, both Brown and Sharp in Providence and Cincinnati Milling Machine Company had transformed from struggling competitors into industry leaders whose American system machines dominated domestic orders while attracting international attention from manufacturers who had previously dismissed American capabilities. Export inquiries arrived regularly from British, German, and Swiss companies seeking equipment that combined European precision with American durability and operator accessibility. The disaster struck without warning on October 15, 1895, when a catastrophic fire consumed Cincinnati's main production facility during the night shift. The morning of October 16, 1895, revealed the full magnitude of Cincinnati's catastrophe in the harsh light of autumn sun filtering through acrid smoke. Fred Holt stood in the charred ruins of his factory, surveying the twisted remains of 47 machines in various stages of completion, their precision ground surfaces warped beyond salvage by temperatures that had exceeded 2,000 degrees Fahrenheit. 3 years of development work lay buried beneath collapsed roof timbers and melted cast iron, while the master patterns for precision castings, the irreplaceable templates that defined every component dimension, had been reduced to ash and slag. The financial devastation matched the physical destruction with mathematical precision that insurance adjusters documented in their preliminary reports. Direct property losses exceeded $60,000, while outstanding orders worth $89,000 hung in commercial limbo as customers faced the choice between indefinite delays or cancellation. The insurance settlement covered only 60% of documented losses, leaving Holtz with debts that threatened immediate bankruptcy and a reputation for reliability that 3 years of careful cultivation had built, but one night's misfortune could destroy entirely. European competitors mobilized with unseemly haste to capitalize on Cincinnati's misfortune, dispatching sales representatives to customers whose orders now faced indefinite postponement. Heinrich Weber, the Swiss-trained foreman who had long questioned American manufacturing methods, summarized the European industry response during a November meeting of the International Machine Tool Association in Leipzig. "This proves American methods are unsustainable," he declared with satisfaction that barely concealed his professional vindication. "Precision requires patience, not shortcuts. These colonial tinkerers have finally learned that superior craftsmanship cannot be rushed or replaced by mechanical gadgets." The criticism stung because it contained uncomfortable elements of truth that Holtz could not entirely dismiss. European manufacturing philosophy emphasized gradual development through incremental improvements tested over generations, while American approaches favored revolutionary changes, implemented rapidly despite limited long-term validation. The fire had destroyed not just machinery and buildings, but the accumulated experience that validated American systematic approaches to precision manufacturing problems. Frederick Geyer, the young German-American investor who had provided crucial financial backing for Cincinnati's expansion, visited the ruined factory on a gray November morning that matched the somber mood pervading American machine tool manufacturing. At 24, Geyer possessed the combination of technical curiosity and business acumen that had made him wealthy through calculated investments in innovative manufacturing enterprises. Standing amid the debris, he delivered advice that reflected conventional business wisdom but missed fundamental realities about industrial innovation. "Maybe the fire's a sign," Geyer suggested, his voice carrying the pragmatic acceptance that characterized successful investors facing major losses. "European methods have worked for decades. Why fight tradition when you can profit by following established patterns?" His proposal made commercial sense: license European designs, import critical components, and rebuild Cincinnati as an American assembly operation for proven Swiss and German machinery. But Holtz understood something that financial advisors and insurance adjusters had missed entirely. The fire had destroyed machinery and buildings, but it could not consume the philosophical breakthrough that separated American manufacturing approaches from European traditions. His revolutionary control systems, precision casting methods, and operator-friendly innovations existed as documented knowledge rather than physical artifacts, and documented knowledge could be recreated more rapidly than European competitors imagined possible. Working from a hastily rented warehouse on the Cincinnati waterfront, Holtz and his core engineering team began reconstruction that embodied American industrial philosophy in its most concentrated form. If overbuilding created mechanical durability that outlasted European equipment, then overengineering the manufacturing process itself should produce similar competitive advantages. Instead of rebuilding according to previous methods, Holtz implemented systematic approaches to knowledge transfer that eliminated the craft-based bottlenecks that limited European production capacity. The innovation extended beyond traditional master-apprentice knowledge systems to include comprehensive documentation of every manufacturing procedure. Written specifications replaced verbal instructions for component manufacturing. Dimensioned drawings eliminated the individual fitting that characterized European assembly methods, and step-by-step procedures allowed any competent mechanic to achieve results previously requiring years of specialized training. The transformation represented industrial democracy applied to manufacturing knowledge itself, making precision techniques accessible to systematic application rather than limiting them to individual expertise accumulated through lengthy apprenticeships. "We're not just building machines," Holtz explained to his engineering team during a January 1896 planning meeting in their temporary quarters. "We're building a system that builds machines." The distinction reflected fundamental philosophical differences between American and European approaches to manufacturing problems. European methods produced superior individual results through superior individual knowledge, while American methods sought superior systematic results through superior organizational knowledge. The rebuilt Cincinnati facility, completed in September 1897, embodied these principles through physical plant design that prioritized systematic efficiency over traditional craftsmanship arrangements. Assembly. Lines replaced individual craftsman stations, with components moving through predetermined sequences that eliminated the random workflow patterns that characterized European workshops. Interchangeable parts manufactured to 1/10,000th of an inch tolerance eliminated the selective fitting that required skilled mechanics, while quality control at every manufacturing stage prevented defects from accumulating into major problems during final assembly. The vindication Holtz had promised came during the Pan American Exposition in Buffalo, New York, during the summer of 1901. The international manufacturing competition attracted entries from 5 nations, with each manufacturer demonstrating their finest equipment under conditions designed to test both precision capability and operational reliability. The challenge specifications seemed designed to favor European approaches, machine a steel block, requiring 23 different operations with final tolerances of 5/10,000ths of an inch, completed in minimum time with maximum accuracy. The competition results validated American systematic approaches with mathematical certainty that even European critics could not dispute. The German Traub machine completed the test piece in 4.2 hours, with final tolerances averaging 7/10,000ths of an inch. The Swiss Micron achieved 3.8 hours with 4/10,000ths accuracy, while the English Herbert required 4.6 hours for 6/10,000ths precision. The French Ernaud struggled to 5.1 hours with 8/10,000ths deviation. Holz's Cincinnati machine demolished European performance standards with results that seemed almost impossible given traditional assumptions about manufacturing capabilities. Completion time measured 2.9 hours with final tolerances averaging 3/10,000ths of an inch, simultaneously faster and more accurate than any European competitor. The achievement represented more than individual mechanical superiority. It demonstrated that American systematic approaches to manufacturing problems could consistently outperform traditional European craftsmanship methods. The ultimate validation came 6 months later, when follow-up inspections revealed the long-term implications of American overbuilding philosophy. European machines required major overhauls after 500 hours of exhibition operation, with bearing replacements, spindle repairs, and control mechanism adjustments that cost hundreds of dollars per machine. The Cincinnati machine maintained its original precision without significant intervention, proving that initial engineering investment produced operational advantages that continued for years beyond the original demonstration.